Good morning, students. I'm teacher Betty, continuing with the nuclear chemistry lesson 3. In lesson 2, we looked at the forces which operate inside the nucleus of an atom. And we said there were mainly two forces, the repulsive force and the attractive forces. Repulsive forces, we said these forces cause repulsion between various protons and hence make the nucleus unstable. Whereas the attractive forces, those ones outweigh the repulsive force and makes the nucleons stable or the nucleus stable. We went further to look at the reasons why small nuclei are more stable than larger nuclei. The reason was larger nuclei are radioactive and they can undergo spontaneous disintegration. We also looked at the factors that affect the stability of the nucleus. We said these were packing fraction, binding energy, magic numbers. You can name them. Today, we are going to look at mass defect. It has been found out that the actual mass of an atom as determined by the mass spectrography is always less than the sum of the masses of all the particles in the nucleus of an atom or the particles in an atom. And these are all the protons, all the neutrons, and all the electrons. If we add the masses of all those particles, they are always less than, they are always more than the mass, the actual mass of the atom. The difference in the masses, that is masses of all the protons, the neutrons, and the electrons, minus the actual mass of the atom is called the mass defect or mass loss. Mass defect, therefore, is equal to the mass of all the protons plus the mass of all the neutrons plus the masses of all the electrons minus the actual atomic mass of the atom. When the nucleons combine to form the nucleus of an atom, mass equal to the mass defect is always lost. How can we calculate the mass defect? An example is oxygen, which has a mass of 15.999491 mu, given mass of a neutron, which is equal to 1.0088665, and mass of a proton is equal to 1.007277, and mass of an electron is equal to 0.0005486 mu. The answer to this activity is, we know that the number of protons are 8 in an oxygen atom. Why? Because the atomic number is always equal to the number of protons in that atom. Now, the number of neutrons are 8. Why? Because atomic mass minus the protons, we are going to get the number of neutrons. Lastly, oxygen has got 8 electrons because the number of protons present in an atom is always equal to the number of electrons in that very atom. Therefore, mass of 8 protons is equal to 8 times the mass of 1 proton, which is equal to 8.0582116, and mass of 8 neutrons is equal to 8 times 1.008665, which is equal to 8.06932. Mass of 8 electrons is equal to 8 times the mass of 1 electron, which is equal to 0.004388. Therefore, the total mass of all the particles in the atom of oxygen is equal to 16.131924. Then we are given that the actual mass of oxygen atom is equal to 15.99491 mu. Therefore, the mass defect is equal to the total mass of all the particles in the oxygen atom minus the actual mass of oxygen, which is equal to 0.137014. Using that information, you will be able to answer activity 7 and 8. Activity 7, calculate the mass defect in the helium atom, which has a mass of 4.0026, given that the mass of a neutron is equal to 1.008665 and mass of one hydrogen is equal to 1.007825. Then activity 8 is requesting us to calculate the atomic number of the element. Given the following information, an element with mass number 15 and isotopic mass 15.004886 has a mass defect of 0.124043. If mass of protons and neutron is 1.008145 and 1.008986 respectively, find out the atomic number of the element. The mass of the electron can be neglected. So another factor was binding energy. When protons and neutrons combine together to form the nucleus, mass is lost. This mass lost is transformed into energy, which is released in the process. The energy released in this way is called the binding energy of the nucleus, or nuclear binding energy. And when the nucleus is broken up into its constituent neutrons and protons, energy is needed. This energy is equal to the binding energy. Binding energy, therefore, is the energy that must be supplied to the nucleus in order to cause it to decompose into its constituent neutrons and protons. It can also be the energy of a neutron or protons required to remove a neutron or a proton from the nucleus. When the mass defect is equal to change in M. Change in M, we said, is the total mass of all the particles in the atom minus the actual mass of that very atom. We get the change in M. Then the mass released in the formation of the nucleus by the combination of neutrons and protons is equal to mass defect times 931.5 mil-electron volts. So 1 mu is equal to 931.5 mil-electron volts. So to convert the mass defect into energy, we multiply by 931.5. Therefore, the binding energy of that very nucleus is equal to the mass defect times 931.5 milli-electron volts. In the case of two or more isotopes having the same mass number, the nucleus of the isotope having higher value of binding energy is more stable than the nucleus of the isotope having lower value of the binding energy. The stability of the nuclei of the isotope having different mass number is compared with the help of the value of their binding energy per nucleon. How do we calculate the binding energy per nucleon? We get the binding energy of the nucleus, then divided by the sum of the protons and the neutrons, or divided by the atomic mass. Therefore, binding energy per nucleon is equal to the binding energy of the nucleons over the number of nucleons in the nucleus, which is the same as, you remember the binding energy is the mass defect times 931.5. So divide by the total mass of protons and neutrons, or total number of protons and neutrons, which is the same as mass defect times 931.5 over the atomic mass. Let us look at activity 9. The observed mass of iron 56 is 55.9375 mu. Using the masses of one proton and one neutron as 1.00732 and 1.00866 respectively, calculate the binding energy per nucleon in milli-electron volts and in joule. Also calculate the energy involved when 1 mole of iron 15 atom are formed from protons and neutrons. We can neglect the mass of the electron. The answer to that activity is, we know that iron 15 contains 26 protons because the atomic number, I already mentioned this, of a given atom is always equal to the number of protons. So it has 26 protons and 30 neutrons, while the atomic mass minus the number of protons will lead us to the neutrons. So it has 30 neutrons. The total mass of these two particles in iron 15, iron 56 is equal to 56.45012. The actual mass of iron 56 given to us is 55.9375. So the mass defect will be the total mass of all the particles minus the actual mass, which is equal to 0.51262. Therefore, the binding energy will be the mass defect times 931.5 milli-electron volts, which is equal to 477.50553 milli-electron volts. So the binding energy per nucleon will be the mass, the binding energy divided by the atomic mass of the given atom, which is 56, and the answer will be 8.5268844. So to convert it into joule, we multiply it by 1.602 times 10 power negative 13. We are multiplying the binding energy per nucleon time by 1.602 times 10 power negative 13. And the answer will be 1.3660068 times 10 power negative 12 joule. Energy released when 1 mole of iron 56 atoms are formed from protons and neutrons. We are going to multiply the binding energy per nucleon by the atomic mass, which is 56, then by the Avogadro's number to convert it into moles. So the answer will be 2875.5382 times 10 power 23 mil electron voltage. So that this is the energy released when 1 mole of iron 56 are formed from, let's see, from protons and neutrons. So another factor was magic number. And this is the nuclear shell model or magic number. This model was proposed by Maria, Winger, and Hans in 1950. According to this model, each nucleon moves in its orbit within the nucleus, independently of other nucleons. And each nucleon is acted upon by the average field produced by the action of other nucleons. The neutrons as well as protons pair among themselves. That is, neutron pair with another neutron, and the protons pair with another proton in the nucleus. These paired nucleons are packed into separate shells called the nuclear shell within the nucleus. A nuclear shell which contains a specific number of neutrons or protons in it is called a filled shell. And this filled shell is more stable than other shells. These specific numbers are 2, 8, 20, 28, 50, 82, and 126. These numbers are called magic numbers. These magic numbers indicate that the nucleons exist in pairs in the nucleus, and the nuclei having either protons or neutrons or both equal to magic number given above are called magic nuclei. And these nuclei are very stable. Being stable, these nuclei are called noble nuclei. The greater stability associated with these nuclei is confirmed by the following facts. These nuclei are found in great abundance in nature as compared to other isotopic forms of the same element. And these nuclei cannot capture neutron because their nuclear shell in their respective nuclei are already filled with the nucleons and hence cannot contain an extra neutron. You know they are always paired. Classification of nuclei having magic numbers. There are mainly two classifications. We have single magic number nuclei and also double magic number nuclei. For the single magic number nuclei, only protons or neutrons are magic numbers. Only one of them is a magic number. Such nuclei can be, we can have an example of oxygen, which is having 8 protons and 9 neutrons, so the magic number is 8. We have tin, which is having 50 protons. We have lead, which is having 82 protons. We have bismuthate, which is having 126 neutrons. Then the other type, which is the double magic number, these ones have got both the protons and neutrons when there are magic numbers. Examples are helium, which is having 2 protons, 2 neutrons. Oxygen 16, which is having 80 protons and 80 neutrons. We have calcium 40, which is having 20 protons and 20 neutrons. Then lead, which is having 82 protons and 126 neutrons. So an assignment I can leave you with is discuss the stability of nucleus under the following headings: neutron-proton ratio, and also odd-even rules. So next time, we are going to look at the nuclear reaction.